All right, great. So I just want to emphasize, very, very rough. I've had a lot of other stuff going on. So I just tried to throw together a little bit of slides, and please just ask me questions, pick on me on this one, and it's going to be kind of a live Q&A. So this topic is meant to be a general discussion about figuring out where we are in space. This is very specifically about spatial localization. And the first thing that I really want to emphasize is the question of what's our datum? Meaning, what is our core position reference? For a lot of applications, including like the rovers, maybe it's the planet that we're on. So very often we're concerned about being located relative to the Earth and some coordinate system that is indexed onto the Earth. In other cases, it's actually a relative coordinate system. And this may be two rovers relative to one another. It may be two humans relative to one another. It may be a human relative to a machine. And this is just kind of a fundamental challenge, is making sure we define what it is we're working relative to. And this gets important because when you're considering things like positioning accuracy and precision and accuracy, you have the kind of standard tolerance stacked up problem that can occur if you're locating things, multiple things relative to one another through a kind of a stack of alignment. So this is just a really fundamental thing, is what is it that we're where's the system boundary, and what are the multiple elements that we're trying to position relative to one another. A really core concept here is the notion of kind of inside out versus outside in. This is actually really oddly, it seems to only be in the VR AR world. I actually don't really hear roboticists say it too much, or people concerned with mapping or robot locomotion. It's I usually hear it in this world of VR and AR, but the concept is very important. And that concept is usually that you have some background infrastructure. In this case, it might be a room or a building or, a planet. And it's do we have sensors or emitters on the infrastructure, these usually stationary objects, or do we have the sensors or emitters on the mobile object, which in this case would be the user in the VR AR case? And this is just a very important distinction for a long list of reasons. Most notably in the VR AR space is cost. It actually turns out to be very hard to convince people to set a bunch of crap up in their house on the walls. And it's also more expensive to do that. So it's way, way superior if you can just have a set of sensors on the user only, and it's only a handful of cameras and sensors. And then there's no required infrastructure. The cost goes down and the overall system complexity just goes down. However, it turns out in terms of technology development, the outside-in approach is usually, it's a lot easier. And the inside-out approach is relatively new and requires a lot more computational power. And the main reason for that is if we don't have a relative datum, or we don't know what that is yet, there becomes this problem that's usually kind of considered like a chicken and egg problem of where are we in relation to something else when we have no known datum or reference point. So for instance, if I have four corners of a room and I put a thing in each corner, and then I go through, there's usually some kind of a calibration sequence in the outside-in approach. Those four things know where they are relative to one another. And then once I start tracking an object, I can then very easily determine where it is. With the inside-out approach, I start with no information about the environment at all whatsoever. So I start simply looking at the first image on a video feed. And from that, I have to now look at that first image and look at things that I think might be stationary. This is the really hard part, is because the environment isn't necessarily completely stationary or structured. So there's potential that if I pick an object that I think is a good thing to look at, it could move. And then I have this challenge of like trying to locate myself relative to things that aren't actually stationary. So this is why I had the Spider-Mans pointing to one another. If we take our first image of the Spider-Man meme and look at the Spider-Mans as like the relative datum, and they start moving, we're going to lose our position. So actually, we need to be looking at the surrounding environment, but from an initial condition perspective, that's very, very hard to determine. So this is where you have a lot of this computation and algorithms behind being like, oh, there's some map point, which is interesting. But if that map point begins to drift, I can downrank it as a contributor to my relative state estimate. And this is what we refer to as simultaneous localization and mapping, is where we create the map and we're also localizing from it at once. The other core thing here is just maybe reminder of like, we're working usually in 3 space. So here's a little brain teaser. If I have, we haven't really talked about, let's not talk about GPS. If I have a point that I'm trying to track in space, if I can measure the distance to that point from 3 other known locations, is that enough information? How many known vectors do I need to determine my position? And so I see a vote. We could do a fingers vote. Mayor, I think this is your vote, Mayor, right?
3.
Victor, Anraj?
I think GPS needs 4.
Because it gives you time. I don't care when it is. It's morning before coffee.
The 3 will still give you the 2-point ambiguity. So to resolve that last degeneracy, I think you need the fork. But if you also have relative, yeah.
And this is simply because we are looking for a 3-space vector, and we fed that 3 scalars. So we need 1 more scalar to close that last degree of freedom. So we get our 3 scalars to define the the vector magnitude, and then we need that last one to define the kind of norm, the direction. And so if we're only measuring distance, it's always n+1. The other way we were usually measuring things in relation to one another, and I'll talk about this in a second, is the relative angle. And this may be counterintuitive. It's like, if I have 3 corners of a room, if I have 4 corners of a room and they have a sensor on them, is it actually useful for me to know the angle that I see the rover within the room relative to those 4 corners? And the answer is yes. That is actually another way that gets used to track things using radio. But I'll talk about that a little bit more in a second. Okay, so I'm just going to jump into the main thing to talk about, which I think is the satellite-based localization, because there's a lot there, and I didn't even scratch the surface. But I don't know, is everybody familiar? Has everybody here used a GPS receiver of any form or a GNSS receiver of any form?
Yeah, but that was 15 years ago for a small robotics project. I was tracking wildlife turtles.
Oh, wow.
Yeah, they were like endangered species. So I had to make a small compact tracker to track the wildlife turtles. Yeah, but
So
that
backpacks.
Yes, but that was still large. So I was really surprised when I saw this small GPS receiver that was just on a fingertip that I posted in the Discord channel. I was really surprised because when I used it, it was like maybe 5 times to 10 times the size of it. So
yeah, for sure. So to talk about satellite-based localization, first of all, we're going to use radio, right? And it's actually, so, I think, so the US was the first to launch up, put some stuff on a launch vehicle and get a constellation. First fun fact about GPS is, do you think the satellites are stationary or not?
Related to what?
The Earth, are they in a geosynchronous or are they in a different orbit?
No,
I think GPS is geosynchronous, right?
no, it's
Nope.
not.
No? Okay.
18,000, it's like half the GPS out, half the geostationary altitude, I think. 18,000 instead of 36.
Yes.
So it's a 12-hour orbit, basically.
Yes. So these satellites, this is kind of an interesting thing to remember. All of these satellites are moving. So if the receiver is stationary, the distance from the satellites are all moving in real time. And this thing is doing all the math to kind of compensate for that. So yeah, GPS is actually, I believe, so the GPS, the US system, it's twice a day is kind of the cadence of the orbit. So US got there first, and then kind of a bunch of countries were like, me too. And we have 4 primary systems that most receivers support, but there are, I think, a couple other ones. I think Japan has one, and India, I believe India also has a handful of satellites that they use in a localization system.
I think Europe also has its own ESA, sends its own GNSS satellites.
That's not besides Galileo?
Yeah, that's Galileo.
Got it. Okay, I was going to say, I thought Galileo was the only one. But yeah, so it's not just GPS. GPS is a subcategory, and the GNSS is the umbrella embodying the entire Earth-based satellite system. And most modern receivers can receive signal from all of these systems concurrently. And actually, forget what the number, GPS is like 26 satellites or so. Well, here's the slide. So in total, if you're using all the systems, it's like around about 100 satellites that you could be listening to. And it is just kind of interesting how the approaches are a little bit different, but the result is very similar between systems. So like, first of all, how does this actually work? So like, how are we measuring distance? It's very simple. So you have a very, very precise clock on the satellite and a precise clock on the receiver, and you have a timestamp of when it was sent, and then you look at the timestamp of when it received, and that gives you kind of like this baseline distance measurement. If you do that alone and you only measure the distance using kind of the baseline system, you can get an accuracy of I believe it's about 15 meters, right? It's about 40 or so feet of baseline accuracy. And actually the largest contributor to that error is the atmosphere itself, because that's kind of the problem here. Is a lot of the terrestrial based localization systems, you don't have this pesky thing of the atmosphere, which creates these multiple layers of undulating, changing noise, and the actual propagation speed through the atmosphere changes pretty rapidly on the time scale of tens of minutes, like the hours or even sub-hour time scale, where you have pretty significant changes, all depending on your relative required level of accuracy. So the first, this is like, we get the GPS satellites up there, we start getting in data, and we look at it, and we're like, okay, we see we have these atmospheric problems, and we need some information about correcting. So what does a correction mean? This is a satellite-based augmentation system. And this very simply means that we have a known datum on the ground, and we pour a big concrete pillar there, and then we put an antenna on that and call that a reference datum. That antenna does not move relative to the thing that we actually care about, which is the Earth. And so if we ask that antenna, where are you over time, and we know where it should be relative to where it's saying it is, that little delta is something that we can publish, and we send it up to a separate satellite outside of the GPS or GNSS constellations. And then depending on whether there are military restrictions or not, and it's encrypted, you get that satellite-based correction data back down onto the receiver. And then you have the delta between where it is and where it thinks it is. And this is usually referred to as differential GPS. These differential GPS approaches are how we get the really, really high accuracies. So that's kind of like a ground station goes all the way up and then comes back down, SBAS approach. And this is pretty old. This has been around for quite a long time. The thing that has changed a lot recently is the cost of these receivers and then the internet connectivity. So GPS was around a bit before we had all this connectivity everywhere. And so these, a local dedicated transmission station or a satellite-based transmission station, a satellite-based transmission were kind of the main options. But now that we have the internet and really ubiquitous coverage, we can start to send that correction data over the internet or a cell modem. And this is where we get the really, really cheap kind of GPS, really high accuracy GPS everywhere, mind you, without having to install a correction station. So let's see here. Oh, let's talk about the issues with GPS. So the number one problem that you'll kind of see is reflections. And the left panel here is actually an extremely expensive problem. The example there is, for various reasons, it's very much in a rideshare company's interest to know which side of the street that you're on. And if you're in the middle of New York City and you have all these tall skyscrapers, those reflections make it extraordinarily difficult to figure out which side of the street you're on. And so this is where you get into all these other kind of approaches to try to correct for reflections or have multiple bands. I should give an overview. GPS comes in a few different flavors. There are two main bands that you'll hear about, L1 and L2. It's pretty easy to remember. So if you see like a modern dual band receiver, it's usually going to be L1, L2. There's kind of a newer band coming into the mix that I think only parts of these constellations support, like specifically the US GPS system. It's relatively new, is L5. And L5 is another band that allows a little bit more robust localization. And the other piece is the frequency, the carrier frequency, it's like 1.2 gigahertz. That frequency is very close between L1 and L2, and it's further away with L1 and L5. And then that can help you kind of get better at estimating how to get through these reflections and things. So that's like a relatively recent development with the GPS system. On the right, we have a GPS denied environment. And this is a GPS denied car tunnel. This is like purely through attenuation, we are denied our GPS signal. In the defense consideration, a big concern there is a GPS denied environment due to jamming. So if you're very concerned about knowing where your dangerous thing is, it's actually really kind of scary to think that somebody could jam your signal and then you don't know where you are. So you'll very frequently hear about the notion of a GPS denied environment, which is usually through jamming, not necessarily through attenuation of like a tunnel, for instance, or a cave, or water. By the way, water also really attenuates those signals very well. So you cannot have GPS underwater. You actually need to fall back to another localization method, is usually what happens when you hear about GPS denied. So once you're in GPS denied, you revert to another localization method, such as some kind of inside out method that would be using SLAM or a pre-learned map of the environment. So there, the example would be like if you have, this is pretty relevant to the kind of space exploration, because we have some pretty good maps of things like the moon and Mars these days. And if we want to land something like the Spirit and Opportunity rover, we teach them the map that we've scanned before and tell them where to land down. That's a GPS denied environment because there's no constellation around those other planets. So we need to have other ways to localize. So we teach them the map and tell them to go to a particular place in the map, and they go ahead and scan the environment using some sensor, whether it be radar or optical. And then we do our localization that way. Okay. Oh, I wanted to bring this up because this is actually becoming a bit more of a like topic these days. So you'll hear UWB thrown around. It's kind of a buzzword kind of a thing. So UWB refers, like, the acronym is ultra wideband. And this very specifically, this has like a rigid technical definition, meaning that the signal is kind of like a, it's an impulse function, meaning that the kind of bandwidth is very, very wide. Is anybody here familiar with the notion of like optical coherence or like low coherence lasers? Just wondering, maybe fishing. So it's like lasers, we always think of them as being monochromatic, right? Like they have one frequency of light that gets emitted from them because they're a resonant cavity. The notion of a low coherence laser is counterintuitive, right? Because we always think of lasers as being very, very coherent. The way that we have a low coherence laser is we actually make it a really, really short pulse. And so throughout the kind of like temporal dimension, if you have a very, high number of waves, that's very high coherence. But if we shorten it down and compress it, and we have like an ultra short laser, this has very low coherence, since it may be like a wave or some fraction of a wave. And this is what we have shown here in this kind of like time amplitude chart, where a UWB pulse is very quick. It's an impulse function, and an impulse function, if you go ahead and decompose that into the frequency domain using your maybe Fourier transform, you'll see that the frequency content is very large, since it has low coherence. And this is what we refer to as ultra wideband. So this is a kind of a shot that I found that lays out some of the particular advantages of that. It can, very robust. You don't have to worry about certain forms of attack on the system. And it also is good at getting around noise, right? Because the frequency content is highly spread across a wide band. So if you have some like little small areas of very high amplitude of noise, your signal is transmitted over a wide bandwidth, and then you can kind of get around that issue. Why is this relative to localization? Many of the new UWB chips coming onto the market, most namely the one that Apple has shipped in the AirTags, have a time of flight measurement feature. And this time of flight measurement feature effectively forms a miniature GPS network, but with objects that you might have around the house. It's the same concept where we're measuring time of flight, just like with GPS and satellites that are around the planet, but instead this is a much, much closer range. And this is actually based on the time of flight of a transmission, not just the signal strength. If you're familiar with something like a tile asset tracker for your car keys or whatever, historically, all of those systems are purely based on signal strength and signal amplitude. And that has a lot of downsides really immediately, right? Because depending on what else do you have in your pocket? It can degrade the amplitude. The human body also has kind of a RF implications, right? We're big bags of salt water. So if we have the asset tracker in our pocket, and if we turn one way or the other, that attenuates the signal. And so we have very, very poor kind of distance measurements purely from amplitude. But a lot of the, there are a lot of applications for like Bluetooth, you'll have Bluetooth beacon tracking. Like if Walmart wants to do some targeted advertising, they'll put a bunch of beacons throughout their store, and then they'll measure the signal strength from the beacon to your phone. And then they'll kind of like watch you walk around using those beacons. But again, the accuracy is very poor, and especially at low relative signal strengths, which is like large distances, it gets very, very, very challenging to measure distance. So UWB is a pretty big deal because it's a time of flight, which is very robust relative to a signal strength-based system. Okay. Okay, so I have a little live demo real quick here. You can track stuff with cameras, and this is kind of what it's all moving towards. Kind of the dawn of autonomous cars. If everybody's watched the DARPA Grand Challenge, there was a lot of LiDAR rangefinders doing a time of flight based. You like strobe the laser, and it wiggles over to the rock, and then it bounces off the rock, and you started your stopwatch when you fired it, and then you stop it when it comes back. That's a time of flight light measurement, and this is how most of the LiDAR scanners work, and that's what we used back in the DARPA Grand Challenge. This is very famously something that Elon Musk is kind of against due to the cost and complexity of these systems, largely because they usually have to have some kind of a rotating scanner. So it's not a solid state system, and this imposes a lot of practical issues, reliability issues. This is a whole tangent I could go on about kind of, LiDAR, the road to solid state LiDAR, the whole thing. I don't know if you've seen the kind of whole thing with Anthony Lewandowski and kind of the Google shenanigans. There was like a LiDAR design that got taken out when it shouldn't have. So LiDAR has a very long and interesting road. But the biggest, I think, advocate to get away from LiDAR is Elon, and he's like, oh, we need to just do cameras. And what we call that is visual odometry. Visual odometry, where we're performing SLAM using just a camera. The live demo I have here is for a Leap Motion hand tracking device. So this is a device that has two cameras. It's a stereo system, and they have a filter that cuts out everything except infrared, and then it's actively illuminated. So there is a pair of LEDs, there's actually 3 LEDs, which illuminate the space here to kind of increase the signal to noise ratio of the hands. And then this is just an extremely high bandwidth. This is, 60 frames per second. Every, 15 to 20 milliseconds, I have an updated pose measuring the distance of my hand. And we also get skeletal tracking through some pretty sophisticated signal processing technology. So this is purely visual. This is a stereo system, which helps give a better depth estimate, right? This is what we use as humans to get a really good depth perception. But this is kind of the performance that can be achieved with cameras and cameras alone. All right. Okay. So that's a little demo. Yeah, so pressure waves, I had mentioned, so this is kind of an interesting thing. I had said that if you're trying to use GPS on the Earth and there's a satellite, kind of in orbit, you have this issue going through the atmosphere. And the atmosphere is a fluctuating, imperfect thing. You have the same set of problems, except like 20 times worse in the ocean. So when you move sound through the ocean, funny thing about sound is it depends on the density. The speed of sound depends on the density of water, and the density of water depends on a bunch of stuff such as like temperature, salinity, very minorly pressure. And so you have these phenomena that can occur where you can actually release a pressure wave and it just gets bent due to gradients in the ocean. And so this is like a whole set of other challenges of using pressure waves to actually look. The kind of defense interest there is obviously nuclear subs. So looking for subs and figuring out, it turns out if you put a sub at a particular depth, it actually becomes like invisible because of the way that sonar bends around in the water. And this is kind of a pretty interesting phenomena of like, it gets very hard to measure things in the ocean. But this is a form of localization that we can use. Shown here is a inside out tracking, right? So if we have a map beforehand and we want to figure out where the boat is, we just have our little scanner and then we can get a very good estimate of where the boat is just by looking at the features on the ground. I'm less familiar, but I have heard of some kind of like deep sea service applications where people will drop sonar beacons. This is just like if we have our Vive HMD from the first slide, we're gonna just drop down some of these beacons onto the ocean floor and they emit a sonar pulse maybe every, 5 seconds or so. The problem with dropping a thing that emits sound into the bottom of the ocean is there's no way to get power to it or very easily recover it. So it's mostly batteries, and you try to maximize your battery life by doing a very, very slow pulse. And beyond that, your ROV or whatever thing that's subsea, it only needs to have an accurate location update, maybe every 5-10 seconds. And then you can, if you're down at the ocean floor, depending on the visibility, of course, you could then use cameras to then do some visual odometry. So there are all kinds of different ways that you can do this and then fuse it together to get a coherent picture. Yes, I wanted to bring up a couple interesting parts. So you'll see RTK come up as an acronym when you read about GNSS receivers. And RTK stands for real-time kinematic. And how I was saying we start at raw GNSS, which is like 15 meters. If we maybe fuse together a lot of satellites at once from the full GNSS system, and then we also have kind of dual band receivers that also helps a little bit to get a faster fix and get a little bit better estimate. A lot of cell phones will be down at the like 5 meter range, 3 to 5 meter kind of error. To get down to the level that will commonly be achieved with RTK, this particular device can achieve a dead reckoning accuracy within about 2 centimeters. And that 2 centimeter accuracy is achieved through a few things at once. So the first is having a ground-based correction station. So use a differential correction station, as I mentioned before. The correction station has to be a lot closer when you're talking about this sub-decimeter accuracy. There are a bunch of, it's actually kind of by state, actually. So in the state of California, as an example, there's a service called NTRIP. And the University of San Diego has a bunch of NTRIP correction stations, which you can email a particular person and they'll give you a free login to subscribe to their NTRIP correction data. And if you're within 10 kilometers, that's the recommended distance. If you're within 10 kilometers of a correction station, you can get that NTRIP correction data and have your 2 centimeters. If you don't have a correction station nearby, what you have to do is install one. And this is a pretty well-established process in agriculture, since a lot of farms are going to be within an order of that 10-kilometer range, and you install one correction station and then it gets beamed out to all of your tractors. lately there's been kind of a shakeup in the business model there because John Deere and the incumbents charge a lot for that correction station. So there are some newer players that are trying to give that correction station over the cell network, since most farms actually are getting cellular coverage these days. So if you don't have to pay John Deere for their, subscription to use your own little tower that you have by your silo, you can just go ahead and get corrections from some local station through a cell link. This is a part I recently used. It's pretty cool. It's very cheap. And you simply can get 2 of them and put one in a fixed position and tell it that it's in a fixed position. And then that one can act as a correction station and beam over to the other one if you don't want to mess with Ntrip. And it works particularly well. The one little unique feature that...
Yes, question. You call this dead reckoning. In what sense is this dead reckoning? Is this 2 centimeter corrected GPS, or is this unrelated to GPS?
This is 2 centimeter absolute latitude and longitude.
But does it use GPS? Because you called it dead reckoning, that's why I'm confused. That's just, to me, gyroscope type things.
Oh, I'm saying, so that is dead reckoning with no additional IMU fusion. So I could speak to that in a second, but when I say dead reckoning, I mean, this is from a cold start.
Oh.
It will know exactly where it is if it can get corrections data. Because again, it's really 2 ingredients. It's the GNSS signals, but then we have to know what the atmosphere is doing. So we need that correction data. The older systems that I mentioned that are the SBAS, you get the correction data from a satellite. In the newer systems, it's provided locally over the internet or a cell link, which is, well, also the internet, but it could be a local Wi-Fi network. It could be a local radio, another different band local radio, or it could be a satellite connection, or it could be an Iridium data connection if you wanted. It could also be a cell connection. As long as you can get back to the internet, you can stream this correction data and get your 2 centimeters. So I said this thing dead reckoning.
At what frequency do you get this accuracy?
This particular part will do 4 hertz. That dead reckoning, so that accuracy is stationary. If you start moving it, that the error increases a little bit, maybe like between 20 up to 50% depending. But stationary, it's sub 2 centimeters. It's like 1 to 2 centimeters. And then as you're moving, it might be like, 3 centimeters or something. So that's a pretty cool part. And this is on a SparkFun board, if you're familiar with SparkFun. But I actually know for a fact this particular U-block silicon that you have here, this little module that they make, finds its way into a lot of very fancy and much more expensive receivers that are skinned up and they look really nice, but the internal is actually just the same module. The other thing I was going to say is an important part of the RTK system is measuring phase. So if you have the wavelength of 1.2 gigahertz or whatever the L1, L2 is, that turns out to be roughly a foot or about 30 centimeters. This becomes kind of like a sampling limit problem, right? Usually your Nyquist frequency, half? You want to be at half. So if we want to be able to measure something that's about a half or a quarter wavelength, we have a serious problem. And if we're talking about 30 centimeters and we want to be at 1/10 of that, we have a fundamental problem. So what we actually need to do here is measure the phase of the wave, and that's what these receivers do. So they actually are measuring the oncoming phase into the antenna as part of the data to determine where it is. So that there's a lot going on, but it's been a long culmination of technologies that have made the GPS this cheap. Okay, maybe this isn't this cheap in the context of some applications, but relative to what it was, you were talking about maybe $1,000, $2,000 or so dollars to get a similar performing device. So this is kind of almost like a 10x thing, I'd say, in the past 5 years or so. Okay. Yeah, so I brought up UWB and how UWB does time of flight. In the consumer electronics space, the other one that you'll hear a lot about is Bluetooth 5.1, 5.2 specification. So Apple has taken a big investment and bet on UWB that does time of flight. Why? I certainly don't know all the deep, maybe more political reasons, but from a technical perspective, measuring the time of flight is very, very robust to a lot of things. And so Bluetooth is the kind of other approach where we're actually measuring the angle of arrival or the angle of departure. And so my earlier mention about how we want to measure where things are, let's revisit the consumer person tracking application, or maybe that's too creepy. Maybe we should be tracking rovers. Okay, this is what we're doing. Now we're in a warehouse, moving around some boxes, and we're tracking rovers, and we want to know where they are. So we put a bunch of little tags around the warehouse, and we can measure the angle that so the tag on the robot emits a ping, and then we have two receivers on the little tag on the wall. And depending on when we see the two waves arrive, right, we have kind of this like wave propagating, and it hits one antenna before the other. We can now measure an angle. And if we add up those angles, which are again scalars, so it would be n+1, we can now determine a position. So there are two different ways of getting a much more accurate position estimate. One involves multiple antennas. The other involves more sensitive and precise clocks. And it's going to be kind of an interesting next 3 years to see who really wins. Apple shipping AirTags, I think, has really put a lot of legs behind the UWB time of flight technology. So we'll have to see how that gets adopted relative to Bluetooth. But it'll be kind of an interesting washout, I think. I'm not sure which way it's going to go. I think it'll probably really shake out to be a cost thing and a licensing thing. I actually don't know how much a UWB costs versus Bluetooth, but this is like a consumer electronics localization thing that's kind of interesting. Oh, I could show what a UWB tag looks like briefly. I had a project where I needed to use some UWB tags. All right, let's see here. So this is a off-the-shelf UWB development kit that you can buy. And just as an example, it's kind of in there. There's this little teeny tag. And these are pretty cool because these are accurate. These are sub-decimeter as well. So these are about $20. So if you want to know where a robot is within a room without using cameras, which again is the modern approach, but if you have some other reason you want to be old school, you could just buy 5 of these tags, put one in each corner of the room, and then strap one onto your rover and know exactly where it is. And it's about 10 hertz, pretty high frequency. So that's another tool that we have today.
And what would that cost us?
They're about $20 a tag. So let me think. I guess for a system that'd be like $100. You would have your 5 tags to get a rover and then 3 base stations. This is again an example of a outside in approach, because you need to know where in this system it calls it an anchor, and you have to label it as an anchor. Kind of the other little fun thing for the Apple example is if you have a bunch of stuff sitting around your house, like keys, for instance, is it an anchor or is it a rover? Is it a base station or is it a rover? It depends, right? Because sometimes your keys are moving, sometimes they're not. Sometimes that means you can use your keys to determine where your phone is in the room relative to the room because they're not moving. But the second that they start moving, you have to vote them down. So this is where it becomes much more complex and fluid in consumer electronics application, where it's like, depending on what's happening, stuff might be moving or stuff might not be moving. And then you have this problem of like, what are we measuring what against? So that's just another, I keep bringing this up because it is a fundamental thing that I don't think people talk about enough, is like, what are we measuring relative to? And especially with these newer, weirder applications, sometimes it's moving and sometimes it's not. All right, so that's what I was able to prepare. Does anybody have any questions?
Can you talk a little bit about Canva-based and optical-based localization?
What specifically?
You mean which type or what to talk about? I want to know if it's any good. How does it compare to using RF-based, things like that?
Certainly. I think the biggest driver today for, at least on the end of low cost, one of the biggest drivers is, again, AR/VR. Facebook has invested an incredible amount of money to make the Oculus Go work really well, to do inside-out tracking within a room. Same thing for Microsoft on the Vive. You can even, these days, you can get really good monocular odometry. So if you have two cameras, like I just showed you in the demo with the Leap Motion peripheral, you can get stereo, which makes depth easier to estimate. But if you have a single camera, you can still do it. And monocular odometry is interesting for the specific application of a cell phone. So probably the furthest ahead there is Apple's ARKit. And they have a really incredible visual odometry going on where you can just walk around and it's now an API call to see where you are in space using monocular visual odometry. For the roboticist, there are some other off-the-shelf things. So I know I'm not as familiar, but I know Ross has some kind of SLAM packages and visual odometry stuff. I think it's not as high performing. It's maybe a little bit flakier compared to something as polished from the fruit company, but maybe somebody could speak. I'm not up to date on Ross's visual odometry and or monocular odometry. And I know there are some SLAM nodes that people have written that are like pretty okay, but maybe not cutting edge. So there's kind of like a few solutions here. You can get just a regular old camera and put it on a computer, and then there are some software tools available which can do the odometry. It may not be as high performance as you want. That's the other question I would have, is how fast does it need to be? The Leap Motion peripheral you saw is doing a complete state estimate every 20 milliseconds. And that's through a lot of work. If you want to have 60 or 90 hertz position estimates, that requires usually some optimization and or some specialized hardware. I know there's a lot of SLAM that runs on CUDA. So if you're going to have a Jetson on your rover, you could get a little bit higher performance running it on the CUDAs. And then I think, I'm trying to think. I actually don't know if there are any good off-the-shelf, completely isolated SLAM modules. Is that what you're looking for? Are you looking for just a camera that you can buy off the shelf for like $100 that you can wave around and it gives you a position?
We're not at the off-the-shelf stage, but that's there's a research component that works, 90% of the time. And when you talk about position and location, sometimes I want to know exactly where I am, but usually I want to know that I'm in the same place that I was yesterday? Or that I'm not in any place that I've been before?
The very common and easy way to do this that you'll see a lot, that a lot of like roboticists doing is they'll use a RUCO tag, a Julia tag, a QR code, and you'll just kind of leave them around. So this is like on cold start, there's this, especially with the inside out visual odometry, it's hard to tell where you are, especially if you're in an area that has a lot of repeat features. So it's like if you're in the suburbs and you look at a house, they all look the same. Which house is it?
Yeah.
If you put some tags around, if the robot can see a tag, it'll know at a rough scale where it is. So like I believe it's a RUCO, please correct me if I'm wrong, but I think that came out of a lab at the University of Michigan. And they, the example there would be like, I'm in some building at the college and all of the professors' offices look the same. But if I put a RUCO tags throughout the building, if I see one, I know that I'm in some hallway number near some door number. And now I have a cold start base layer of truth of where I am. This may not give me an exact sub-decimeter position, but it gives me kind of like the city level, like the state, city, and town, right? Not the street, but it's like the state, city, town. Does that answer the questions concerning figuring out where I am if I have a camera? The other one I'll mention that's kind of interesting is I said it's in everybody's, well, it's in a lot of tech companies' interest to know which side of the street you're on. So there has been some efforts to make it possible to just send a photo to a server somewhere, and then the server tells you exactly where you are in the city, purely from the skyscrapers that it sees. So this allows you to just do this, right? You're in your Uber app and you tip your phone up and it takes a photo using the front facing or rear facing camera. And it sees, you know, the Seinfeld corner cafe in the background. And it's like, I know exactly where you are. But that's kind of a service that is increasingly becoming more common. The other one that was getting used for a while is called Skyhook, or well, maybe I should correct myself. I think Skyhook was the provider name. I think they're still around. Yeah, so Skyhook's thing was when I was a kid, I had this hobby where I would kind of walk around scanning for Wi-Fi SSIDs. This is usually referred to as war driving. I wasn't doing it in a black hat sense, right? I wasn't doing anything. I was just very curious. And it turns out if you're inside of a building, GPS just like really sucks and doesn't do a good job. So the thing that you can see in the RF spectrum inside of a building are all of these SSIDs from wireless routers. Now, each wireless router has a unique MAC address. And this MAC address is kind of guaranteed unique. You can always spoof them, but most people are, you know, good players and they're getting an off the shelf from Cisco or Linksys or whoever. So each individual Wi-Fi base station has a unique identifier. And if you just do a scan using your Wi-Fi radio, because most things today have a Wi-Fi radio, you can use the, again, signal strength. There's no time of flight or angle of arrival, but purely based on the signal strength, you can get a rough estimate of where you are if you know what to look for. So Skyhook's whole service was, they did kind of like what I was doing when I was a little kid, except they have an immense database, like a huge database of almost every device that's, you know, visible publicly. And then when I come home with my iPhone sees my wireless home router and that MAC address, that can go up to a service somewhere. And once I send that MAC address back up, it says, oh, you're near this GPS coordinate. Because by the way, my phone also has a GPS receiver. And when I drive by in a car, I scan a GPS coordinate and a MAC address, and now they're linked.
So I'll ask another question. Can you say something more about the difference between indoor navigation using localization and outdoor navigation using localization? I mean, Mars is all outdoors, but maybe the underground caves we live in are indoors.
Yeah, I don't have a pithy response to that. Besides, I'm the very practical consideration there is simply just how harsh the environment is. So, as an example, in an indoor application, cameras are much friendlier because there's like fewer bugs to get splatted onto them and cover them, and dust and dirt to deal with, or mud or grease. In a application such as, farming, mining, these things that are very dirty environments, cameras become challenging. As humans, we have this really incredible like self-wipe system that keeps our cameras clean all day long. And we have just a way to keep our cameras working really great and free of debris. We have not, to my knowledge, ever taught a robot how to do this. A lot of the autonomous car people, I think, are probably going to have a little anti-bug cleaning station. Maybe it's a little robot refresh area. The robot goes to visit the robots to get its bugs wiped. But what I'm getting at is outdoor is really dirty, and RF is great for that because GPS antennas are just like a plastic box. And it's okay if they get a little dirt on them and mud on them. So they're just extraordinarily robust. The camera stuff, not to say that it isn't robust, but this is a real consideration. The one example I might give that's a real implication of this that I thought was kind of crazy when I was younger was the notion that the Sojourner rover, one of the first US landers, was having a lot. Well, actually, no, I take that back. I believe it was Spirit. I think it was Spirit. So it had a planned mission life. And a lot of the concern there was literally dust getting on the solar panels. And it turns out that there was a Martian kind of windstorm that cleaned the solar panels. And this extended the mission life purely on having a kind of like unplanned self-cleaning action. So this is just an example of how primitive our like most sophisticated robot was, that it didn't even have a way to clean itself. I mean, if you have a fly in your house that's annoying you, watch what that thing does when it lands. It has a self-cleaning function. It can clean off its wings, it can clean off its cameras, its eyes, using its appendages. And this expensive rover that we sent some countless number of miles away doesn't have any way to wipe off its panels and get itself some more juice. I say all this purely on the consideration of like dust is a serious problem for cameras. And there are mitigations, like again, Tesla is using cameras. A lot of car manufacturers are also using cameras for lane assist. And some mitigation is like it's on the windshield, so the slope is really steep. So stuff like bugs and stuff that get splatted on the windshield don't cover it up as extremely. It's harder for that to happen. You can also have the cameras pointing backwards, so they're not on the wind impact area. But yeah, outdoor cameras are a little bit rougher. RF is more stable. Indoors, satellite signal gets blocked, so you have to have local RF. And then once you're in water, all bets are off. No RF gets through water. Very little light gets through water. So you're stuck with pressure waves. But then pressure waves are challenging because they bend and they do all these crazy things. And this is why, this is part of the reason, but this is part of the reason why we have very little information about the bottom of the ocean. It's such a harsh environment, and it's so hard to get to, and it's so hard to measure because nothing gets down there. And that's why it's just as mysterious as like surfaces of other bodies.
Yeah, the one more sensor that could be used is radar. I've seen at least when the wavelength in the visual spectrum doesn't work. You could use like the RF wavelengths. And I was researching few of the sensors because the light, when you are in an icy environment here in Finland, so many of the optical systems stop working. So you use radar for localization.
Yes. I probably should have. I mean, don't forget, radar and LiDAR are like, radio is light, right? Like radar emits photons. They're just not visible. So radar is also another form of light. It's just very, very long wavelengths. But yes, radar localization, this is a pretty standard thing for spacecraft. I believe the Skytrain system that dropped down the most recent lander used radar and, with a map. And so we said, go here, and it used its radar to view the planet and then find its place. Radar is nice because it has better punch. It penetrates stuff. So this is why also in the automotive application, that radar that's hidden behind the bumper is nice because if the dirt gets on the front of it, it's okay. The radar can still go through the dirt.
There's a related thing I wanted to bring up, which is you have this inside out versus outside in ways of doing localization. I think there's another dimension that you've sort of talked about, but not explicitly, which is I would think of it as content-based versus address-based. So using a networking analogy, so using landmarks like the skyscrapers around you, or in ancient times like the constellations, even modern satellites, they have these things called star trackers. Like when they first are injected into orbit, they have like a little telescope that points at stars. And I'm trying to think of other examples. The most extreme example I can think of is Pioneer 11, that plaque it had, which Carl Sagan designed. I know you guys must have seen it. It has a engraving of a man, a woman, and like a weird diagram with Earth and like, I think 11 directions. Those are distance encodings to well-known pulsars. So that was a very interesting example of localization. It's meant—
The Voyager? The golden record? The Voyager golden record?
Pioneer 11, not Voyager. I think it's Pioneer. Yeah.
Sorry. Yeah.
Yeah, so this is fascinating to me because it's the most extreme case, because it's to allow aliens to figure out where Earth is. And I think there's actually a science fiction story and some aliens figure out where we are based on that and come attack us. I forget which one it is. But basically the localization system there are these pulsars with characteristic emission frequencies. And this diagram shows Earth's location in relation to those pulsars. And in order to get to a standard measurement system, it uses the 21 centimeter hydrogen wavelength of the electron transition as the measuring stick. And that to me is like as extreme as you can get in like a completely self-contained, I would call content-based localization. So by content-based, I'm using that phrase specifically because if you look at networking, people talk about address-based networking as like, TCP/IP addresses or MAC addresses, things like that. Content-based is where is a particular file. If you have a hash of a file, you shouldn't have to know where it's located. You should be able to like just ask the internet, give me the file which corresponds to this hash, which is a function of its content. And then it'll tell you where it is and deliver a copy. And I think anything based on landmarks in localization is kind of a version of that. And the kind of extreme version I was thinking of is, for example, in my rover that I'm building, I was thinking of attaching a little microscope to it that'll just examine the patch of carpet it's over right now. Now, carpet is this completely uniform surface, but I presume that if you take like little cellular photographs of the carpet, like every inch, like a grid thing, there'll be just enough unique fingerprint-like characteristics that if you sort of do the right kind of machine learning on it, you should be able to look at that and say, fingerprint hash, I'm on this patch of carpet. So this to me is taking the skyscraper or constellation approach to the max by taking advantage of sort of the content-based hashability of the environment. So I don't know what environments are friendly to this. Probably carpets, probably things like rocky fields or deserts where there's a dust problem, yes, but there's also going to be like pebbles and stuff that probably have a fingerprint-like structure. The sky is pretty good, constellations, especially in outer space. So I feel like there's a whole direction of approaches there that have not been adequately explored, where you do completely based on like landmarks, and like the extreme of landmark would be everything is a hash.
Yeah, just a comment based on that. Do you know what fiducials are?
No, what is that?
It's like fiducials are markers that you place, and they are like easy to identify. So if you see on the rovers that are sent to, for example, Curiosity, you'll see a specific marker. I'll post the link in Discord.
Okay.
So they are specific markers that help in identifying specific parts of the rover. And then you could also have specific SLAM based on rovers for visual odometry. So the camera is easily able to identify these markers. So these markers are called fiducials. So you place them for easy understanding of the scene.
Okay, so I think I'm trying to generalize that concept to, can you use the environment itself as a sort of natural terrain of these fiduciary objects, as you're calling them. So it feels like that should be a whole dimension. So just like inside out, outside in, you should also have address based versus content based, where the reason I think this approach is interesting is it should be much more robust. Like you're talking about, all right, maybe you just look at objects around you and some of them might move some of the time. Like maybe my rover takes pictures of the room around it and says the computer is there, the bookshelf is there, but then I move the bookshelf. But because it's robustly orienting around a bunch of like these fingerprintable objects, it sort of is a little bit noise resistant. So I'm trying to see how far can you push that, because to me, it seems like that's slightly, it might be rougher, but it seems more robust. And if you can compensate for, like, maybe you don't need super high accuracy. If you're just trying to get from, okay, here's an example. Like, suppose we are all in the same city and I'm trying to say, deliver a package to Victor. Now, that's a conceptual position and I'm at a conceptual position. I don't need the precise GPS. All I actually need is a package delivered to wherever Victor happens to be at this point. And Victor is a recognizable object. I'm a recognizable object. You can navigate between us through a whole bunch of recognizable objects. So how much do you actually need absolute localization in space? Because depending on the application, you might not need it at all. Like if you're building a map, sure. But if you're doing delivery, if you're doing like, even like things like agricultural applications, if you're trying to like water a field and it's like water every plant that's sprouting, it's like you need to know where the plants are. You don't need the exact X and Y coordinates. So it feels like localization, maybe we don't need as much accuracy as we think, and we need kind of precision of application specific precision. I'm sort of wandering all over now, but
well, this is exactly why I brought up, what are we, like, this is the Spidey meme. What are we relating ourselves in relation? It's all relative, right? So is it in relation to some pulsar? Is it relation to the sun, the planet, you versus me? Like there's a lot of different, one of my favorite ones. So I think I'm not sure if this might be kind of a tall tale, but it's more than, let's call it a thought experiment. So I have heard, this is kind of a rumor. I have heard that, so insects are very, very dependent on this notion. It's usually referred to as part of visual. So if visual odometry is the superset, one of the ways that we determine our position is through structure from motion in a monocular system. And this is like a lot of prey animals that don't have a very front-facing eyes, right? They're wide-facing to get a wide field of view. One thing that they do is they'll move. And this is to get a bit more of a depth perception, to get more of a structure from motion. So if you have a monocular system, there's no way to determine depth without seeing the parallax shift as you move. So this is where the structure from motion arises. Insects use the environment to help them control their like attitude in flight. And I have heard that this is a thing that can happen if an insect loses reference frame through the visual system. They become unstable in flight. And there are very, very, very few places where this can occur naturally. And the one place where I've heard that it could potentially occur is over a perfectly still pond, where it's a complete reflection. And depending on how bright the stars are, you may or may not be able to do star tracking as well. But this is like a potential place where an insect could lose control authority and crash because of the lack of relative kind of like visual anchors. You always have the horizon line, right? But again, sometimes depending on where it is, it can be really, really hard.
Well, regarding insects, I've been told that if you hang up plastic bags full of water, it gets rid of the insects. And you're now describing the mechanisms. If you have a clear plastic bag full of water, it acts like one of these perfect mirrors as the insect gets closer. So maybe you have to make the bag correctly.
Maybe I'll try this. I actually am very curious if this works now. So this is a visual system jammer for insects, and then they lose control authority and crash. Interesting. Oh, here's another localization example referring to Venkatesh is like, what is the minimum kind of viable thing? So really, really high speed and high performance localization sensor that we all take for granted these days are mouse sensors in like computer mice. These are very, very specific and extremely high performance devices these days. They have a ultra specific camera sensor and specific front end optics to illuminate using a microscope kind of objective the surface that it's on. And then they just have some really, really high speed. I think a lot of these sensors are operating at like tens of like single kilohertz range, like thousands of frames per second. And they just look for like a really bright fleck of dust. And then as it moves in and out of the frame, it just follows the really bright fleck of dust. And this is a pretty simple thing, right? And it's all relative. So once the high contrast ROI, like region of interest, comes into the frame, it writes a box around it, and then you just track it frame to frame, and you get your XY signal that you send up the USB bus. But this is an example of a sensor that's become extremely cheap and extremely specialized that does this high-speed localization on a 2D planar surface. All right.
All right, any other thoughts on GPS localization?
Does anybody have the AirTag yet? I haven't bought any to play with.
I have the tile. I got a free tile, and I used it for a while on my keychain. Then the battery died, and I never bothered to replace it.
Tile is likely going to be out of business very soon.
Yeah, if Apple has done it, Android will be pretty close behind. And I think, yeah, it's sort of a transient business model.
Especially because the battery is replaceable in the AirTags. So this whole model of recurring revenue in a completely sealed system is, yeah, they don't do that on the AirTag.
Tile does have a more expensive model, with the battery replaceable, but it's like too much trouble to just manage another ecosystem of devices to manage your existing ecosystem. It's kind of like a natural thing to get absorbed into the devices themselves. So I'm kind of glad this is happening, actually. Yeah.
I do have one, I think, aside, because yeah, actually that brings up a good point, Venkatesh, talking about networking in the world of networking. Kind of an interesting one there is IPv6. If anybody's familiar with the IPv4 versus IPv6 system. No. In short, the internet, kind of like the internet protocol concerns of IP addresses, and the address space is not big enough to support every device that exists on the internet today, and the address space has been exhausted. So the usual approach is the little Wi-Fi router that you have at your house forms an internal network, and then it has what is called NAT, network address translation, where there are internal network addresses and then public internet addresses, and they're different address spaces. This gets around the lack of available addresses. IPv6 goes from being a 32-bit address, which is, I don't know, however many billions of nodes. It goes from 32 bits to 128 bits. That's like some big, 10 to the large number of addresses. This effectively means that every single device that we will make that has a network interface for the next probably 100,000 years or whatever will have a unique address. The issue there is if you give your phone or your computer an IPv6 address that's unique on the internet, there's a huge security risk there. And there's a huge ability to track you risk there. So this is a localization thing that actually becomes a privacy threat. And the mitigation in the IPv6 system is to have a randomized address. So most modern phones and computers follow a kind of like IPv6 security protocol where they recycle and go through an address randomly just to protect you from getting tracked. The AirTags actually also have the first measure of security that I've seen on any other similar product, because like a tile doesn't do this. One risk is that somebody puts a tile on you without your consent, whether it be on your car, like your backpack, so on and so forth, and it can very inconspicuous place. And then they use the tile tracking service to track your person. Apple has gone through a bunch of measures to make that really hard. And part of this is your phone, there's no way you can turn it off. So your phone is always looking for AirTags. And if it sees an AirTag within range that's not yours, it'll tell you that there's an AirTag that seems to be suspiciously always following you. And then you can go find it. So this is kind of like an interesting localization security consideration that's kind of like increasingly becoming a bigger topic.
What
Even better, you need a phone to protect yourself from other people tracking you.
That's the irony, right? It's like buy an iPhone to see people tracking you.
It's better. I can detect if the car behind me has been following me for the last 5 blocks. Why should I be limited to AirTags? The phones know each other. You can tell me, the guy with an iPhone been following you for the last 5 blocks.
I mean, we also haven't spoken about plate readers. I have a whole fun story about somebody who stole a car and then swapped their license plate with mine. That's actually super effective to evade law enforcement, like extremely effective. They thought I was the guy for a minute.
Listen, 26 years ago, I got a phone call in the middle of the night. It's the police. Is your car license plate number such and such? Yes, it is. Where is your car? So I look out the window. I say, it's parked under my house. They say, thank you. So they caught somebody.
Yeah. I got a different call. It was a similar call, but they're like, did you like surrender your license plates? And I'm like, yeah, I think so. And they're like, if you haven't surrendered your license plate, you'll get pulled over at gunpoint. I'm like, okay. I hope whatever, because I handed it over to the DMV, but whatever the DMV people are doing, I hope they didn't put it on one of their cars or something. But yeah, so like localization with license plates is a real thing, and that's its own set of kind of like a societal concern with localization as it's becoming really easy.
On that note, have you guys seen what3words.com? I saw this several years back. I'll post a link here. It assigns a unique triple of 3 words to any location on Earth. So it's a startup trying to build a localization service based on like a weird text-based addressing scheme. It's I don't quite see the point of it, but it's really funny. And like New York City Hall is clip apples leap. So you can find 3 words by just putting your location. So I thought it was just a curious example of localization.
Hashing. Yeah, hashing.
Yeah. So this is related to what I was suggesting, that the entire environment's map can be hashed in like a finite element way. This is more kind of like a discrete point set way of doing that. But it feels like there's some sort of almost merging of network-based location and space-based location paradigms. There's almost a merging happening. Like you're always somewhere in 3-dimensional continuous space, and you're always somewhere in relation to a bunch of random networks that are interpenetrating. And it's like something interesting is happening at the intersection of those 2 kinds of notions of location. So, and I think products like this What 3 Words are trying to like be in that intersection somehow. Okay, we are 10 minutes past 11. That's going to be a big recording file, an hour and a half or something. But any last thought?
Recording.
Yeah. Oh, you stopped it. Okay.